Vectors. So last time we did eigenvalues and eigenvectors of 2 by 2 matrices. Today we're going to do eigenvalues of 3 by 3 matrices. Now, these could get quite tricky. Now, in all examples we will do in this course, lambda is going to be a common factor, or it's going to be obvious that there's a repeated bracket you can take out at some point. So synthetic division is not needed. Now, you can tell it's not needed because you can take out a common factor if it looks like this. Right, because you can see that there's no constant term here, plus 7 or whatever. So you can just take out a common factor of lambda, and then it would just become a simple trinomial. Right, now we need to remember some stuff from matrices in order for this stuff to work, but hopefully as I go through it, you remember all that stuff. So, example number 1, find all the eigenvalues and eigenvectors of A, which is matrix 1, 2, 1, 6, negative 1, 0, negative 1, negative 2, negative 1. Now, first thing, I've decided I'm going to work out the eigenvalues because you need those before you can work out the eigenvectors. So I've written down my eigenvalue equation. The determinant of A take away lambda I is equal to 0. Now remember, all that means is we take away lambda from each element in our matrix. Right? So then, this is the bit we need to remember how to do it. Now it's all about finding the determinant of a 3 by 3 matrix. Now what we do is remember that element's positive, that element's negative, that element's positive, because it's a matrix question and each element of a matrix has its own sign. So I've got 1 take away lambda, and I'm going to multiply that by the determinant of the matrix, not of that, the elements not in that row, not in that column. Negative 1 take away lambda, 0, negative 2, and negative 1 take away lambda. And that element there is negative, so that's negative 2, or take away, we would do to get the... Then we've got it not in this row and not in this column, so that's 6, 0, negative 1, negative 1 take away lambda, and then plus 1 multiplied by 6, negative 1 take away lambda, negative 1, negative 2, just like that. So just done in the same way that we did the determinants before. I know there's a wee bit of extra algebra in here because you've got these lambda terms, which are really just x terms that we've been doing in anything else. And remember that we're saying that's equal to 0. Right. All my ones keep disappearing. Right. The negative sign, so if they do that, then it's just because the software is deciding that it doesn't like them. Right. So then that means I've got 1 take away lambda, and remember it's AD take away BC. And negative 2 multiplied by 0 would just be 0. Take away 2, and then we're doing AD take away BC, so that's 6 multiplied by negative 1 take away lambda, and again negative 1 times 0 would be 0, so that should take away 0. Then we've got plus 1, and then we've got 6 times negative 2, which is negative 12, take away negative 1 multiplied by negative 1 take away lambda. So you've got to watch here with your negative signs because things can get a wee bit hairy down here. We're saying that that's all equal to 0. So let's start multiplying stuff out and hopefully... So negative 1 multiplied by negative 1 is 1. Negative 1 is lambda, it's plus lambda. Negative 1 times negative lambda again is plus lambda. Negative lambda times negative lambda is lambda squared. And the 0 is just gone. Right, negative 2. And then you've got negative 6. Take away 6 lambda. So I always work out the stuff in the brackets first. Right, that bracket there, that bracket there, and that bracket there, just in case. Is it a nice little easy out for us? It's going to make things easier. Not in this case, I don't think there is. Right, so that's negative 12. I'm just going to make that plus 1. Negative 1, take away lambda. That's equal to 0. Right, so let's keep going. And remember, always tidy everything up before you start doing any other multiplication of brackets, because if you don't do that, it ends up, that's where mistakes are made. I'm just going to leave this bracket the way it is just now. Like that. Okay. Now I can simplify that bit, but I'll do that in a minute. Right. So let's multiply this bracket here. So that's going to 1 times 1 is 1 plus 2 lambda plus lambda squared. So I've just multiplied everything by 1. Then I've got negative lambda times 1, which is negative lambda. Negative lambda times negative 2 lambda is negative 2 lambda squared. And negative lambda is negative lambda cubed. Right, here, plus 12 lambda. Here, that is just, well, that's negative 13, so that's going to be take away 13 and take away lambda is equal to 0. Okay, now that looks a wee bit messy and a wee bit horrible, but let's just write it the way we would normally write something. And we would normally write something with the lambda cubed first. So I've got negative lambda cubed. We tend to write the highest power first, right? Then lambda squared, I've got negative 2 lambda squared and plus lambda squared. So that's just going to be negative 1 lambda squared, which is negative lambda squared. 2 lambda plus 12 lambda is 14 lambda. Take away lambda is 12 lambda. Okay, so 2 take away lambda is 1 lambda plus 12 lambda is 13 lambda, take away 1 lambda is 12 lambda, right? And then we've got 1 plus 12 is 13, take away 13 is 0. So I'm just left with that little equation there. Now, what I don't like is the fact that that's got a negative at the start. Now, remembering in maths, if you want to change the sign of one thing, you just change the sign of everything in the equation. And you can do that in any equation, and it's particularly useful when it's equal to 0. So I'm just going to change the sign of everything. Right, so that's going to give me lambda cubed plus lambda squared, take away 12 lambda equals 0. Right, and that's me multiplied out all my brackets. Let me just put that in, see if the computer software has missed any of this stuff out. That looks fine to me. Right, so this is the point at which we do CDT. It's when we did CDT for the 2x2 matrices. So it's when we're going to do CDT for 3x3 matrices. Right, is there a common factor here? Yeah, there is. Lambda appears in all parts of that. So I'm going to take out a common factor of lambda. Take out a common factor of lambda. Then in my brackets goes lambda squared plus lambda take away 12. So I'm just taking a lambda out of each part of it and putting it in the outside is equal to 0. So I've done my common factor, right? Is it a difference of 2 squares? No, because this bit here has got 3 terms. Is it a trinomial? Yes, it is, because there's 3 terms in that question. So this is when everyone starts messing up, when you move the thing up and down. Right, so I'm adding, make plus 1 here, because it's plus 1 lambda, and I'm multiplying to make negative 12. So that means one's positive and one's negative. Well, it's either 1 times 12, 2 times 6, or 3 times 4. Right? Which pair of these, with one being positive and one being negative, adds to give me negative 1? It's not that. Oh, it must be that. So that's going to be negative 3 and plus 4. Right? Simple as that. Then we just separate out our 3 bits. So that means that lambda is equal to 0. That means that lambda take away 3 must be equal to 0. And that bit there means that lambda plus 4 must be equal to 0, because that's what we always do when something's factorised. Because all you're essentially saying is, well, what do these have to be in order for that to be 0? Well, one of them has to be 0, all of them have to be 0, whatever. So you move that over 3, and lambda equals negative 4. And there we go. Those are our 3 eigenvalues. But that's us done in terms of eigenvalues. But you didn't think it was going to be as easy as that. I said these are the most questions you've got to do the most amount of work. Don't think anything's difficult about what you've got to do. Maybe multiplying out all those brackets and making sure there's not a mistake, but it's just a long, right. Okay, let's find out the eigenvectors this time. So we're going to get an eigenvector for each eigenvalue. Now in the assessment or in an assignment I give you, you only need to work out one of the eigenvectors. But what I'm doing is I'm just going to do all 3, because effectively what that does is it gives you 3 examples of how to find an eigenvector in a 3 by 3 matrix. Right, so our first eigenvector is going to happen when lambda equals 0, because that's our first eigenvalue. Okay, so then we get out our eigenvector equation. The eigenvector equation is basically that your matrix multiplied by x1, x2, and this time x3 is equal to 0. It could be x, y, and z, but we tend to use x1, x2, x3, or x1 and x2 for eigenvalues. So in 2 by 2, we only had x1 and x2 because there was only 2 rows in our matrix. Now we've got 3 rows and 3 columns in our matrix, it's going to be x3. Right, so remember what we do is we just take our matrix that we took the lambda away from. So it was 1 take away lambda, 2, 1, 6, negative 1 take away lambda, 0, negative 1, negative 2, and negative 1 take away lambda. That was our matrix that we had. Now, all we're going to do is we're going to take our lambda away. But our lambda is just 0 this time, so it's just going to keep our matrix the same. So it's going to be 1 take away 0, 2, 1, 6, negative 1 take away 0, 0, negative 1, negative 2, negative 1 take away 0. Make that a wee bit neater if I can. Right, as I said to you last week, this drawing tablet thing is great in a way, but it's nowhere near as good as something like Apple Pencil or one of those Microsoft Surface tabs we can actually see as you write. Okay, so that means that I've got 1, 2, 1, 6, negative 1, 0, negative 1, negative 2, negative 1. And I want to solve this system of equations. Now, what I want to do is make this upper triangular. Right? So what that means is I want the bottom 3 elements of my matrix this time in that corner to be 0. Like that. Doesn't matter what the rest of the stuff is. Element there, element there, element there, element there, element there, and element there. Doesn't matter what those are, but I need to make these 3 0. Now these other ones can be 0 as well, but as long as these ones are 0, it's upper triangular and I can find the eigenvectors. So in order to do that, make this element 0, you've got to use R1 and R2. In order to make this element 0, you use R1 and R3. In order to make this one 0, you all use R2 and R3. Right? That's the way you've got to do these things, because if you don't do it in that way, it'll end up just being the same thing over and over again. It'll just go around in a cycle. So to make this element in the middle row 0, use R1 and R2. To make the bottom corner element 0, use R1 and R3. And to make the one in the bottom row in the middle 0, use R2 and R3. If you don't do it that way, effectively it just breaks this bottom corner element and it stops it from working. Right, I'm going to take this wee diagram away just now because otherwise I'm not going to fit everything in. Right, so I'm just going to make upper triangular. Right, so that means my top row, I'm going to call that row 1, row 2 and row 3. Now, it's not going to affect this thing here, it just affects this matrix here, just like we did in the 2 by 2. So the top line stays the same. Right? Now, in order to make this element 0, it needs to be R2 take away 6 lots of R1. Because 6 take away 6 lots of 1 would be 0. So that would be 0. So I'd do that to everything. So negative 1 take away 6 lots of that would be negative 13. Then that take away 6 lots of that would be negative 6. Okay, I'll just put x1, x2, x3 in here. Right, now my bottom row, I need to make this one here 0. So if I just do, hold on, that should be negative 2. Computer's missed a wee bit out for me again. Right, so if I just do R3 plus R1, so because negative 1 plus 1 would be 0. So R3 plus R1, that plus that is 0. That plus that happens to be 0. And that plus that happens to be 0. So in 2 moves, I've actually got my bottom 3 elements here to be 0. So I'm done. I don't need to use R2 and R3 to make this one 0 because it already is. And that will happen in most cases with these eigenvectors. Sometimes it doesn't, and if it doesn't, I'll show you what to do later on, but it will pretty much in every single case. Okay. Right, so now we've got to decide what we're going to do with this. Right now, this bottom row doesn't tell us anything, it's just like the 2 by 2. It tells me 0x1 plus 0x2 plus 0x3 equals 0. Well, that doesn't tell me anything about what x1, x2 and x3 are. But this row here does. So row 2 tells me 0x1 take away 13 x2 take away 6 x3 is equal to 0. Right, so negative 13 x2 is equal to, if I move that across, 6 x3. Right, and then remember, what we do is we check and see if we can simplify 13 and 6. No, we can't. So that tells me that x2 equals 6, because remember, it's always a number in front of the corresponding element, and x3 is negative 13. So I know already my matrix, my eigenvector looks like this: 6, negative 13, but I'm missing a wee element from the top here, so I need to work out what that is. So in order to work that out, I'm going to use that top line there. So x1 plus 2x2 plus x3 equals 0. Now, good thing is, I know already that x2 is 6 and x3 is negative 13. So I'm just going to substitute those in. So x1 plus 2 times 6 plus negative 13 equals 0. So that's x1, that's going to be take away 1, is equal to 0. So x1, move that across, is equal to 1. So my eigenvector is just 1, 6, negative 13, but remember we write it as put this t in because basically as long as they're related in this way, the vector can be any length. So another eigenvector would be the same, would be 2, 12, negative 26. If you multiply it by any number and those three stay in the same ratio, it's the same eigenvector. So the eigenvector when lambda equals 0 is t of 1, 6, negative 13. Right, so that's one of my eigenvectors. Second one is when lambda equals negative 4. You remember that was my next eigenvalue. I suppose it might have been 3, but it doesn't matter, it's the same thing. Right, so we write down our matrix. So that's 1 take away lambda to 1, 6, negative 1 take away lambda, 0, negative 1, negative 2, negative 1 take away lambda, x1, x2, x3, 0. But this time we're substituting a negative 4 into here. So that's 1 take away negative 4, 2, 1, 6, negative 1 take away negative 4, 0, negative 1, negative 2, negative 1 take away negative 4. As you try and make sure everything lines up underneath, but as I said, writing on this is not as easy as it may look. Right. And as again my negatives have disappeared, I wonder why it does that. It's done it here as well. It's very odd. I seem to do it all the time. Anyway. So 1, that becomes plus, that's 5, to 1, 6, that's negative 1. So negative 1 plus 4 would be 3. negative 1, negative 2, three, x1, x2, x3 is equal to 0. Right, let me just check my answer. Let me make sure I've not made any mistakes because of the disappearing lines. No, that looks fine to me. Right. Right, so I think paper was maybe better. Didn't have all this mad stuff disappearing all the time. Right, so first thing I want to do is I want to make this element in here 0. So to do that, well, if I do 5 lots of R2, take away 6 lots of R1, because the lowest number that's on both the 5 and the 6 times table is 30. So if I did 5 times that would give me 30, take away 30, so that would give me 0 in there. Okay, so that's, oh sorry, maybe written that a wee bit too soon. So I should have written my new matrix first. Doesn't matter, I'm going to have to do that next bit in a minute anyway. The top line always stays the same. 5, 2, 1, and I'll move that wee dot because more than likely I'm going to think that's a negative at some point. Right, so as I said, I want to do 5R2, take away 6R1, and I do that to everything. That's going to be 0, so that's going to be 15, take away 12 is 3, and negative 6. Then here, I want to make this one in here 0, so if I do 5R3 plus R1, because remember, this one here is always got to be R2 and R1, this one here is always got to be R3 and R1, it's the only way it works. So that's going to give me 0. 5 lots of that is negative 10, plus that would be negative 8. 5 lots, that would be 15, plus that is going to be 16. So there we go. I've got my new matrix. Now, I'm not finished this one because I don't have this element being 0. So I'm going to have to do an extra little bit of row reduction. As I said, we did this in Gaussian elimination in matrices, and I'm sure some of you hated it, but that's why I spoke about it then, because I knew it was going to be coming up in a way at this part of the course. So now the middle line's fine as well. It's only this bottom line here that I need to do something with, and it's because that's not 0. So I need to make this one 0, and I need to use R2 and R1. Sorry, R2 and R3. Right now, if I multiply those together, I get 24. So if I do 3R3 plus 8R2, right? 3 of these would be negative 24, plus 8 of those, that would be 24, so that would give me 0, so that's right. So 0, 0, right. And then if I do 3 of these would be 48, take away 48 would be 0 as well. So again, I've got my upper triangular matrix, which means those bottom 3 corner elements are 0. Okay, so then again the bottom row is not telling me anything, but the middle row does. So that's 0x1 plus 3x2 take away 6x3 is equal to 0. So 3x2 equals 6x3. Now those are both in the 3 times table, so that they can just be simplified. So x2 is equal to 2x3. And remember, it doesn't, see in the previous question there was a negative on one side and a negative on the other. It doesn't matter. As long as one of them's negative and one of them's positive, it's the same vector. Okay, so that means that x2 is 2, and x3, well, the number in front of that is 1. So my eigenvector just now, t, are 2 and 1. I need to work out what that element there is. Right, so go to my top row of my matrix. So 5x1 is 2x2 plus x3 is equal to 0. Right, and let's substitute in the things I know. So 5x1 plus 2 times 2 plus 1 equals 0. So it's like it's going to give me a nice answer here. Five x1 plus 5 is equal to 0. So 5x1 equals negative 5. So x1 is just negative 1. Solving an equation like normal, so that means your eigenvector is that. So your eigenvector when lambda equals negative 4 is t negative 1. Now, see your answers. It depends on the working of how you've done your question. There's no, because eigenvectors are general, for example, if I had 1, negative 2, negative 1 there, it would be the same eigenvector and it would be fine. So see if it's the negatives are different, that's fine. Right, it's still the same eigenvector. If I look at that previous one I've just done, I got 1, 6, negative 13. If that eigenvector was negative 1, negative 6, positive 13, it's the exact same eigenvector because that t would just be negative 1. So it doesn't matter, right? That t always stays t. And if the signs are different between the answer and what you've got, it doesn't matter. It's the same vector, so don't worry about it. Right? That's just a wee thing. I'll just put that there just so you can, or I could have had t of negative 1, negative 6, 13, because that's the same answer. I'll never put 1. If I put that down, it would be the same answer. Just I know that that's a very common question that comes up as we're doing it, and just I thought I would say that as I was doing it. So I would only give that top answer, but if you gave that answer, it's the exact same thing. Same in this one. If my numbers came out and I got 1, negative 2, negative 1, it's the same thing. It doesn't make a difference. You'll get the same answer. Anyway. Okay, right, let's do the last one. That is, oh, missed it, n lambda equals 3. You'd think I've remembered the matrix by now, but I haven't. So we've got 1 take away lambda, 2, 1, 6, negative 1 take away lambda, 0, negative 1, negative 2, negative 1 take away lambda, x1, x2, x3 is equal to 0. Okay, so then what we do is We substitute our 3. So I'm just going to do it without, right, so that's going to be negative 2, 2, 1, 6, negative 4, 0, negative 1, negative 2, negative 4, x1, x2, x equals 0. Okay, watch all those negative signs change. Oh, there we go, one gone there. Half that letter is gone. Anyway, so I need to make this element here 0 first of all. So top row stays the same as always, negative 2, 2, 1. Right, so I need to make this element 0. So if I do 2 lots of that plus 6 lots of that, 2r2 plus 6r1. Because remember, this element here is always r1 and r2. So give me 0. 2 of that is negative 8. Plus 6, that's 12, so that gives me 4. No, it wouldn't. Oh, decided to do it slightly differently. Okay. Right. 2 of that plus 6, that would be 4. Yep. And 2 of that plus 6, that would be 6. Another way you could have done it is r2 plus 3r1. That's how I did it last year. Anyway, it doesn't make a difference. It's the same thing. If you want to do it like that, then you can. Right. Then I need to make this one in here 0. So if I do 2r3, take away r1. 2 of that would be negative 2. Take away, yep, would be 0. So negative 4, that would be negative 6. And negative 2, that would be negative 9. Is equal to 0. So I'm nearly there. I've just got to make this element in here 0. Our top 2 lines are fine. So if I do 4 of that plus 6 of that, or I could do 2 of that plus 3 of that, whatever you want to do. I'm going to give you the same answer. Right, so that's 0, 0, 36. Oh, what's happened here? That's a negative 9. Negative's falling off again. Right, so that's negative 39 plus 36 is negative 3. Negative 39 plus 36 is negative 3. Yeah, that's right. Okay, so we've got a slightly different setup. We've still got our bottom three elements there being 0, which is what the question asked me. So from this bottom equation, I've got 0x1 plus 0x2. Looks like a 6, change that. Take away 3x3 is equal to 0. So that just means that negative 3x3 equals 0, which tells me that x3 0 divided by negative 3, which is just 0. Cool. Easy stuff. Right, then. Now, if I then use this here, I would get the 0 eigenvector, so I've not to do that. Right, so if x3 0, we must use the top line rather top row rather than the middle row, so we avoid getting the 0 eigenvector, because the 0 eigenvector doesn't do anything for us. Right? It's not useful in any way. It would be wrong to have the 0 eigenvector for this, right? So as soon as you've got a value, as soon as you find out that x3 is equal to 0, you ignore the middle row and you jump straight into the top row. Right, so negative 2x1 plus 2x2 plus x3. Right, but we know x3 is equal to 0. So negative 2x1 equals negative 2x2. I can simplify those both. Those are both, I can divide them both by negative 2, so that just means that x1 equals x2, or 1x1 equals 1x2. So x1 equals 1, and x2 equals 1. x2 equals 1, x1 equals 1. So my eigenvector lambda equals 3 as t1, 1, 0. Again, as I've said to you before, if you got it to come out and it was, that's exactly the same thing. So it does make a difference. If all that's different in your vector is the signs, you've got the right eigenvector. It's just written in a different, you've just decided to write it differently to the answer in the back of the book, or the answer that's on a sheet of paper, right? Whatever you choose to do. Okay, so you've seen how long these questions take. As I said, you'll only be asked to work out eigenvectors and the eigenvalues and then one eigenvector, but it's good practice to try all of them. So what I've done is, this is effectively 6 questions, because I want you to work out all the eigenvalues, and then I want you to work out all the eigenvectors for each one. Now I've put the eigenvalues here, 0, 4 and negative 5, and then the corresponding eigenvectors underneath. And then the second one here, I've put the eigenvalues here and the corresponding eigenvectors underneath as well. So if you can do that, you'll have absolutely no problem doing a question like this in the assignment. We've got one thing left to do in eigenvalues and eigenvectors. As I said, I'm just going to give you a brief introduction. I'm not looking to go into too much depth, and that is diagonalising a matrix. We'll look at diagonalising a matrix tomorrow. I'll put it up by the end of the week, and then that means we've only got double integration to go. Double integration, again, I'm just going to give you a brief overview of. I'm not going to go into too much detail, just so you've seen it before. It'll be useful for you when you go to uni, but I'm not going to go into too much depth because we're nearly at the end of May already. I'll put the revision sheets and assignments out as soon as I've written the assignment. But I hope everyone's well, and if you get any questions, please just ask me on Microsoft Teams. Thank you.